Dr. Mohammed, and this is a new video regarding the ASCE seismic provisions. Load. We're going to talk today about the load combinations and load direction. Give more details about these two main points in the previous slides, in the next slide, sorry. Okay, so now let's go with the load combinations. First of all, I'd like to highlight what is the ASCE-7 16, the version 2016, is telling us about the strength design load combination. I'm going to concentrate on the strength, okay, not the allowable stress. So the basic combination with seismic load effects, this is under section 2.3.6, okay. So actually they are giving us the load combinations, and it seems that there is a kind of modification, as you can see with this gray line in the left. This means that there is modification compared to the previous version, which was 2010. Actually, the main load combination that we are going to use here, they are the load combination itself number is going to be 6 and 7. Before it was like 5 and 7. They are concerned with earthquake, but now it is 6 and 7, and it is as usual 1.2 dead plus EV, which is the vertical load component, plus EH, the horizontal earthquake load component, plus life load 0.2 S, the snow load. This is one combination, and the other one is 0.9 dead load minus EV plus EH. Okay, so this is the case of the load combinations, including earthquake effect. Where the seismic load effect is going to deal with overstrength, in this case we are going to use the horizontal load combination to be EMH. So this is the maximum load for with the inclusion of overstrength, as we are going to talk and see later on. Okay, there is no effect for EV regarding overstrength, okay, so it is only regarding the horizontal component. Okay, so now what is the concept of the EV vertical and horizontal? It may be helpful to recognize that the quantities EH and EV are the effects of loads, not the loads themselves. This is very important concept here. They are effects of loads, not the load itself. Okay, so EH, it means that the effect of the horizontal load of the earthquake, and this is the effect from the vertical load of the earthquake. So maybe the effect of the vertical load, it might produce horizontal loading, and the effect of the horizontal loading of the earthquake might produce vertical loading. Okay, so this is the point. They can be tension or compression, axial forces, shear, bending moments, or torsional moments. For a one-story shear wall, if we're going to talk about shear wall, application of the horizontal seismic forces, which is EH, causes overturning moment and shear. That's logic, right, for shear wall from horizontal load combination, both of which are coming from EH. So this is moment and this is shear from the same horizontal. Okay, the factor 0.2 SDS times the gravity load, dead load, corresponds to EV. So EV is commonly, we put it like 0.2 SDS, the design short period, or design for short period, SDS. Okay, load effect that increases or decreases the axial force in the wall, right? The factor 0.2 SDS times the gravity load corresponds to an EV load effect that increases or decreases the axial force in the wall. In this simple example, an EH force or moment is never added directly to EV. That's right, because EH, as we said, it is what? It is moment or shear, but EV, it is axial force. So they are not even the same element, which is shear wall. They are different types of straining actions. But sometimes for bracing, for example, this was for wall here, okay, the case for the wall. But here for bracing, you're going to find that for an individual brace, application of the horizontal seismic force from V causes brace force that has both horizontal and vertical components. And the factor 0.2 SDS, which is the vertical, times the dead load, also has horizontal and vertical. This means that for bracing, the effect of EH and EV are going to be added. Okay, they are going to be added together. We are having horizontal and vertical components of accident. In this case, the brace force is based on exactly EH plus or minus EV. Okay, so this is the main difference between the two. This is the main difference between the two. Okay, now we understand this this point. Now let's go to the next slide, which is related to 0.2 SDS concept and effect. Why we take this 0.2 SDS? Vertical acceleration, this is the vertical acceleration effect, is required to be considered in the design of all members of a structure, even though they are not part of the seismic force resisting system. So whenever that we have the earthquake that is coming from the soil, it has, as we said, horizontal and vertical one. So we need to design our structure for this vertical component. Okay, for example, design of gravity load resisting system for pre-stressed concrete girder may be governed by the dead and earthquake condition. So if we have a girder and this girder is pre-stressed, okay, take care, it is not monolithic, it is pre-stressed concrete girder. It would be governed by the dead and the earthquake condition, where 0.2 SDSD, this one, is subtracted from the dead load, because we have like 0.9 dead load and it is going to be minus 0.2 SDS. This is in the load combination number 7, as we have seen before. So this would be this could be a controlling condition, especially for the tension at the top of the girder. Here it will be the controlling condition because the dead load is the minimum, and it is, as we said, it is what? Pre-stressed. So the dead load, whenever that it is minimum, this would make a problem, and maybe it is a controlling condition for pre-stressed concrete girders. EH effect with overstrength. Certain structural elements or actions such as collectors, especially collectors. I'm going to talk about collectors later, okay, in detail. So collector, that just remember that they are like elements collecting the loads from the main lateral resisting systems whenever there is discontinuities or something. In seismic design categories C through F, so A and B are excluded here. Or whenever that we are talking about columns supporting discontinuous walls, so we have collectors, we have columns that is supporting discontinuous walls, are required to be designed for seismic load combinations with overstrength. So now we can understand the meaning of the overstrength when we can use it. In such cases, the seismic load effect, EM, which is the maximum, has its horizontal component multiplied by the overstrength factor. Okay, we're going to see it shortly. So we're going to see this shortly in the overstrength. I'm going to show it to you here. Okay, anyway, we are going to see this overstrength load combination maybe at the end of the video. Only one exception here that is talking about the cantilever. Maybe it's not related directly to this title, but it is related to the cantilever. Whenever that we have a cantilever, we say that we are going to apply vertical load, which is including 1.2 times the gravity or gravitational acceleration. It is upward only. This is why to take into consideration the dynamic effect of the vertical loading case, the vertical loading case. which is due to the earthquake. So if we have a building, okay, and this building there is a kind of a cantilever here, for example, so we need to design it for a vertical upward upward force that results from an effective vertical acceleration equals to 1.2 g times gravity, gravitational acceleration. This is to provide some minimum strength in the upward direction and to account for possible dynamic amplification of vertical ground motions resulting from the vertical flexibility of the cantilever. So because the cantilever is flexible in the upward direction, then we need to guarantee that it will not fail. But in the downward, there is nothing like this because already it's loaded with the original loading here, so no need to take care of this. Okay, the requirements is not applied to the downward forces on cantilevers for which the typical load combinations are used. Okay, now strength design load combination, the strength design load combination in ASC. Actually, this is ASCE-10, what I'm going to talk about. They are similar, very similar. Only remember that in ASCE-10, this is combination called combination 5. But it is the same combination as combination 6 and ASCE-16. And 7, it is the same as before. And where we can find this combination, you can find this in chapter 2 of ASCE. Okay, there are strengths and allowable stress-based design. Okay, so you are going to see it in 232. Okay, you are going to find 7 basic load combination under this section, and you can recall this section. For any given member, such a reinforced concrete girder, different combinations may be found to control the different aspects of design. That's right. If we have a beam, for example, we're going to find that the bottom and the middle, it is going to be controlled by combination number 2, which is gravitational. However, the top ends of the girder, it is going to control by maybe load combination 5, which is this load combination, for example. Okay, so the same element can be designed for different load combinations. Okay. A specific example of this circumstance is provided later. The remainder of this example concentrates on 5 and 7 because we're going to find an example later, actually. It is only an explanation, not an example. Okay. Anyway, as you can see, this is 1.2 dead and 1 E and 1 live load and 0.2 S. I'm going to talk about why this is 1 and so on. Okay, first of all, you can see that we have 1 earthquake, 1 year. Means that there is no load factor is actually multiplied by E. This is why, because E has been created or calibrated to be consistent with the ultimate load, okay, with LRFD, for example. So this is why we use E. But in the stress design, you are going to find it multiplied by 0.7, I guess, or something like this. So it is 1 because it is already calibrated based on the with an ultimate load. Okay, this factor of 1 for live load, it could be reduced to 0.5 based on special cases. What is very interesting is 0.9 here. Why that the dead load should be reduced by 0.9. Whenever that we have stabilizing effect from earthquake or wind added to gravitational loading, then gravity load should be reduced by 10%. Okay, so this is something that is important and we need to keep in our mind. Another thing is sometimes this is for ASCE. Sometimes other building codes like IBC, for example, the 2012 IBC specifies a factor of 0.7 on snow load in combination for combination 5, which is this combination. So here, instead of 0.2, it is 0.7. Why? What is the reason for this? For configuration that do not shed snow off of the structure, such as sawtooth roofs. If we have sawtooth roofs, like something like this, so the snow, whenever it comes, it accumulates and it is not like shed off the sides of the building, then this factor should be 0.7, not 0.2. This means that IBC supersedes the ASE regarding the combination, so take care of this. As we are going to see also, like ASIC, American Institute for Steel Construction 306, and also ACI 318, they are superseding ASCE. Maybe they can put or add additional load combination that you should respect whenever that you are designing the component. Okay, now let's go to another point regarding the combination, the most important two combinations that we are having. We said here the snow load in combination 5 is always included whenever S is larger than 0. There might also be snow load effect in E in both combination. Actually here, even that we do not have S, but actually S is included here in the dead load, where because the effective seismic weight here, the effective seismic weight is required to include 20% of the design snow load when the flat roof snow load exceeds 30 pounds per foot squared. Yes, I'm sorry, it's not in D. I'm sorry, it should be in E. It's not in D. It is in E. In E because E, it is related to the seismic weight, and the seismic weight includes some portion of the snow load in case of the flat roof, which is 20% of it. So already snow load is included here, even that it's not explicitly written in the equation. Okay, and as I said, 0.9 factor applies specifically to the case in which the structural actions due to lateral forces and gravity loads counteract on one another. That's right. Whenever that you have a building under earthquake that it moves in this direction, and there is like something like overturning, for example, gravity loads or dead load tries to counteract this. Whenever there's counteract action, then 0.9 is going to be used. Dead load or the stabilizing force from the gravity should be reduced by 10%. I think it is related to probability. Like we are not sure that 100% of the dead load is going to work for us. Maybe 10% is not going to work because of spooling of concrete, maybe some issue. I think it is related to probability. I couldn't find directly what is the reason for the reduction, but it's understandable. It's something that we can understand. Okay. Ways for applying the design load combination. We have two ways actually for the application. The first, which is covered under section 12.4.2, applies to all elements and connections. We are going to design all of the elements and connections in the structure and may be considered the standard load combinations. The second, covered in section 12.4.3, is for those special elements. We're talking about special elements here. Do you remember what we mentioned about the collectors and the columns that is supporting discontinuous walls? They are considered to be special elements or connections that must be designed with overstrength factor. We need to work with overstrength factor in this case. Okay. ASCE provides several specific cases where the overstrength load combination must be used. What are the cases where that we need to use overstrength factor? So we have different cases actually. Here there are like 4 different examples here. So we have, for example, under these sections, we have like the foundation and other elements contributing to the overturning resistance of cantilever column structures. If we have cantilever column structures, okay, in this case, overturning resisting column cantilever, the foundation of it, the foundation of, if we have like a foundation of a cantilever column, okay, then in this case the the overturning resistance is going to be controlled by the foundation. In this case, this is very critical. The idea here under the overstrengths, as I have mentioned before, they are critical elements. These critical elements, we need them to work elastically. So if we have a cantilever that is, its failure is dependent upon the foundation, then this foundation should be elastic. We're not going to put ourselves in a dangerous situation by allowing inelasticity here or something. No, we need it to be like elastic. Another case where that elements supporting discontinuous walls or frames, these elements, they are going to be crucial for the continuity of the walls and the frames. So they need to be designed elastically. So we are going to multiply their load combination by the overstrength. Collector elements, their splices and their connections, also they need to be designed with the special load combination including overstrengths, and you can find this in section 12.10.2.1. Chapter 14, which triggers the use of material standards such as ASIC for steel and ACI for concrete, and other material standards that trigger the use of overstrength factor and load combination. Actually, these codes, they can give some indication or give some in sections saying that we need this element to be designed with the inclusion of overstrength. Okay. Now let's go and see what is the meaning of E and load combination 5 and 7. So E, actually it should be EH plus EV or EH minus EV. Okay, so it is plus here or minus. So where EH, so the horizontal component is always going to be the redundancy factor multiplied by QE. QE, it is the component force, which is maybe a moment, maybe shear, maybe axial force. It is the component straining action force. Okay, and rho, it is the redundancy factor. I'm going to talk, already I've talked about the redundancy factor in the previous video. Please revisit it and you're going to understand. So remember that EH, it is going to be related to rho. And here, if we are going to have overstrength factor, then we are going to replace rho with omega. So we're going to use omega in this case instead of rho if we are going to design our special element. For the vertical component, it is usually equals to 0.2 SDS times D. It is a component, the vertical component, taken as a 0.2 SDS times D. Okay? So these are the main components of the earthquake, the horizontal and the vertical one. For the horizontal, as we said, it equals to rho times QE. The term EH represents the horizontal seismic load effect. The term rho is the redundancy factor computed in accordance with section 12.3.4. You can revisit this section. This value is 1, which is rho. We are talking about rho now. It is 1 for all buildings assigned to seismic design category B or C, and is either 1 or 1.3 for seismic design category from D to F. So now if we have B or C, of course A, for our A, we are not designing for seismic, just we are applying 0.01%, 1% of the weight, that's it. And for B and C, we're going to take it 1, and is either 1 or 1.3 for some cases between seismic design category D and F based on the circumstance or the condition. This factor applies to entire structure but may be different in the two orthogonal direction. Take care of this. So maybe we have the structure, we have rho here equal to 1, but we have rho in this direction equal to 1.3, because rho, it is 1 or 1.3 only. Okay, and it is for what? Take care of this word, entire structure. So do not be confused with the redundancy factor and the overstrength factor. They are totally different. Redundancy is using for the entire components, entire structure elements, for the lateral load resisting elements. Okay, overstrength, it is totally different. It is for specific loading or specific elements in the structure that we need them to work elastically. But redundancy, it is totally different. It is the street analogy that I have explained in the previous video. Please revisit it with the streets and number of streets and so on. You are going to understand the philosophy behind redundancy from the previous video. Okay? Okay. For EV, it is 0.2 SDSD. As we said, this is the vertical component. So the term EV represents the vertical ground acceleration, which is not considered explicitly elsewhere. It is not found elsewhere, okay? With the exception, there is only one exception, and section 12.4.4, which provides requirements for minimum upward forces in horizontal cantilevers for buildings in SDC D through F, which already I have mentioned here. Do you remember from previous 4 or 5 slides, I was mentioning about the cantilever? Do you remember this? So the cantilever, it is only one exception. If we have a cantilever, then we need to apply 1.2 G, the gravitational acceleration upward. That's it. That's it, only because of the flexibility of the cantilever and the upward direction. That's it. Okay. Now let's go to the next one. EH, it should take, as we said, this rho, which is the redundancy factor, and QE. What is QE? It is the seismic effect on individual member or connection. We are talking about QE. It is the individual element or connection, quantity. Seismic analysis of the structure produces this value, which includes direct loading, application of equivalent lateral force, accidental torsion amplification if applicable, and orthogonal loading effects if applicable. Okay. So QE might represent, for example, a bending moment at a column support, an axial force in a bracing member, or a stress in a weld. Okay, so it is individual component. In some cases, QE might represent an interaction effect, such as an axial force bending moment combination in a beam column. In such cases, both the axial force and bending moment occur concurrently, and should be taken from the same load combination. That's true and understandable. Okay. Yes, here this is the case where that we use the redundancy factor in our case. Okay, and this is the case where that the vertical component is adding, and this is the case where that the vertical component is subtracting from the dead load. Okay. So this is very critical for foundation, for example. Okay, this is the basic load combination for simple frame. This is the case where that the plus here and 0.2 SD adding up. So this is load combination 5, we call it heavy gravity. And this is the case of light gravity where that 0.9 minus 0.0 SDC. As we said, this is heavy gravity is important for foundation, for example, and axial force columns. This one is going to be critical for the cases where that we are having a uplift on one support coming from the earthquake, as we are going to see. Okay, this is a case for the load coming from the east. And this is the case where the lateral load is coming from the west, because we have different load combinations. Load cases, not load combination, that I'm going to show it to you now. This is the combination of basic combinations for worst effect. This is coming from load combination 5. As you can see, it is coming heavy gravity with lateral east, so the force is coming from this direction. And this is heavy gravity with lateral west, which is the load coming from this direction. The circled one is the controlling moment. This is the controlling moment. So in this beam, at this end, 10 is controlling. And the middle, it is 4. Okay, similar if it is in the west. However, if you are going to go to load combination 7, for example, you're going to find that here the controlling is 4, because here it was 2, but here it is 4. So you can understand that load combination 5 can produce the controlling moment at the left of the girders, however that it couldn't give the controlling moment on the right of the girder. But load combination 7 did. It is 4 here. And similar also in this corner, it is here the light gravity with lateral east. Okay, so it is coming from here. This is the controlling moment. So this means that load combination 5 and 7, they are important, both of them. Okay, now let's go to the next, which is the basic load lateral loads cases for equivalent lateral force. We are having 16 cases. They are easy actually, not difficult, but if we have a plan like this, we have L and we have B, and this is the north direction. So the cases that we need to apply is, if we are assuming that we are going to apply two simultaneous load direction, we are going to talk about the load direction in minutes. So we need to apply the force from the east, this is the east-west direction, with some eccentricity here. There is some eccentricity here, as you can see. And the others, so here they are from the east with the eccentricity, and then they are from the east. This is positive eccentricity here, above the center, and here it is below the center. Okay, so we have 4 cases. And in this 4 cases, we have the orthogonal load effect is going to be 0.3 of the VNS, which is the load, earthquake load in this direction, 0.3 of it. Why 0.3? I'm going to explain it later in the load direction, so don't worry about this. Just I want you to know that we have 16 load cases. Okay? So we have here, this is 4, and another 4 where that from the west direction, but this is positive, eccentricity positive, and here this is negative, and here this is negative. So we have 8. We have 8 now, where that the eccentricity is coming from the main component. Now we are going to have another 8 when that the eccentricity is coming from the, the minor component, which is the north-south component. So I have eccentricity here, positive, and then we have another one negative here. And then another 4 opposite to these. So we have total of 16. We have 16 load case that you should check for your structure. Okay, 16 load cases. Okay, now let's go to the contradiction of load combination. I call it contradiction, but it is not contradiction. Sometimes there are some loading that is you do not know. For example, if we have a member in an intermediate moment frame that has a wind-based design force that is twice as high as the seismic design force, would be sized on the basis of the wind forces. So it would be sized, means that the size of the cross section, if we call about the beam, so the size itself is going to be based on the larger load, which is the wind load twice. However, but must be detailed according to the requirements of the intermediate moment frames. The detailing itself, the steel and so on, and the stirrups should follow the requirements for intermediate moment frames. Okay, so this is the meaning of the contradiction. If we have like 2 different loading conditions, one coming from the wind and it's twice, and one coming from the earthquake, which one that we should apply? So you need to satisfy both. Okay, the size should be based on the higher load, and the detailing should be following the earthquake. Okay, special seismic load combination, when that we can apply it, including overstrength factor. So actually in the sometimes ASCE says, as I said, for collectors and for some columns, it requires the overstrength factor to be included. How it is going to be included here? Okay, do you remember that when I said that it is going to replace the rho, it replaces rho here, and we have omega times QE and omega here times QE. Maybe it would come from ASCE, or maybe it can come from something or another specification, material specification, like ACI or AISC. Maybe they stipulate some overstrengths. For example, ASCE, okay, requires that the use of the overstrength factor include elements supporting discontinuous walls or frames, and the design of diaphragms collectors. So as we said, elements like columns that is supporting discontinuous walls or frames, and the diaphragm collectors, they are very important in ASCE and they give it special care. However, for other specification, material specification, for example in AISC, it says, it is very clear, for moment connection, for intermediate moment frames, they should be designed for shear forces. We're talking about the shear forces that are determined by using load combinations stipulated by the applied building code, including amplified seismic load. The word amplified means that omega. That's it. That's the meaning of it. So this is an AISC. Now another thing also in AISC, similar provision exists for steel columns and anchor rods. They said that amplified seismic load is defined as the horizontal component of earthquake load E multiplied by omega. Okay, so this is another the specification, which is ASCE gives in different two spots that the requirements of omega should be used in the combinations. Okay. Now overstrength versus redundancy. I hope that you do not mix the two. Okay. The only difference with respect to the standard load combination is that the overstrength replaces the redundancy. Load combinations, including the overstrength factor, are required only for few select members or selected members in connection. As we said, those are very few and they are going to be critical for the structure, and we want them to behave elastically. However, most members and connections are designed using the standard load combination. The standard load combination means what? Rho is there. Redundancy factor is going to be included. In no circumstance are both the redundancy factor and the overstrength factor used at the same time. You cannot say that I'm going to use rho plus the omega in the same time. No, it wouldn't happen. Okay, this one or this one, redundancy is commonly used, overstrength rarely used. Okay, or used only for special elements. Okay, now let's go to the load directions. Load directions, which is talking about the direction of loading, whether that it is going to be from this side or both or whatever. So actually load directions in general, it is the earthquake loads coming from different directions. We are not guaranteeing anything. So the point is, we need, whenever that we design, to be sure that the effect of the loading coming in the worst case direction. So maybe we can apply two simultaneous load direction at the same time. The orthogonal combination procedure combines the effect from 100% of the seismic load applied in one direction with 30% of the seismic load applied in the perpendicular direction. This is the common case, like 100% here and 30% here. For horizontal structure elements such as beams and slabs, they are not important to think about the orthogonality for the beams and slab. So here 100, and for example here it is 30%. It is not important for the slabs and beams. Okay, but it is important for what? Yes, for columns. Orthogonal effects may be minimal. However, for vertical elements, which means columns or shear walls of seismic force resisting system that participate in both orthogonal direction the design likely will be governed by these combinations, because if we have a plan here and we have a column here in the corner, if we have component from here and component from here, this is 100, this is 30%. This is going to be the worst point, because it would receive from the 30% and 100%. So this means that it would be a controlling load combination for it, or the direction of the loads is going to be controlled by this load configuration. Okay. Now let's go to the next. So the load direction for structures in SDCB, the analysis including accidental torsion effects may be performed independently. That's important. Independently in each direction. So we are going to take one time here and another time here, and the structure may be designed on that basis. However, for higher SDC, starting from C, D, E, and F, and so on, the direction of load effects must be explicitly considered wherever a type 5 horizontal non-parallel system irregularity occurs. This is very common type of irregularity. Almost 90% or 80% of the structures, they are falling into this type 5. So this means that we need to consider the simultaneous application of loading. Because such irregularities are common, many buildings must be designed for complicated combination of loads that include gravity, lateral load acting from any direction, simultaneous application of lateral loads acting in orthogonal directions, and accidental torsion with or without amplification. Okay, so these are the cases where that the load direction is going to be applied. Okay. Okay, so this is the cases for the equivalent lateral force analysis. We said that 16 load cases, as we said. So we put it in a table here. So we said that the major load direction, east-west positive and negative, and north-south positive and negative. So each one, it has two of them. This is major load applied with eccentricity. 0.05A, this is the direction perpendicular to the loading. This is B. AX is the torsional amplification factor. So torsional amplification factor. And B, it is the direction that is perpendicular to the loading itself. So this is maybe here. This is the orthogonal load applied to 0 eccentricity, 0.3 minus or positive for all of them. If you count them, you are going to find 16. It is very similar to what we have explained, the plan that I have explained a few slides ago. Okay. Now, this is only the last thing that I'm going to talk about, and with a couple slides after it. It is from the code, just to know what is the direction of loading. From the code, they said that there is a criteria for application for the direction of loading, as we said. For seismic design category B, the design seismic forces are permitted to be applied independently. Take care of this, independently, in each of the two orthogonal direction, and orthogonal interaction effects are permitted to be neglected. So we're not going to consider anything. We are going to have one earthquake from here, that the load from here and the load from here, and then independently, whatever the element that is going to be designed from this, design it once here and design it once here, whether that it work or not. Okay, independently. That's the point. For seismic design category C, loading applied to structure, okay, shall as minimum conform to the requirements of this section, okay, and the requirements of this section. So what are the requirements of this section? So here, this is a minimum that this should be applied, but there is something additional that should be considered. What are the additional things? That structure with non-parallel system irregularities, which is the most common one, structure that have horizontal structure irregularity type 5, in table 212.3-1 shall use one of the following procedures. So we have procedure 1A or B. So in A, if we are going, the structure shall be analyzed using equivalent lateral force, okay, or modal response spectrum analysis, MRSA, or linear response history procedure, okay. Now linear only, linear response history procedure. It's not nonlinear. Take care. As permitted under section 12.6 with loading applied independently in any two orthogonal directions. So we can apply the load independently. One time here, one time here. It is okay. Okay, but look here. The requirements of section 12.5.1, which is that the worst case scenario, this is the meaning of it, is deemed satisfied if members and their foundations, so it is not members only, it is foundation as well, are designed for 100% of the forces for one direction plus 30% of the forces for the perpendicular direction. The combination requiring the maximum component strength shall be used. So here means that if we have a column here, and the axial force is coming from this column due to 100% of the earthquake, for example, it was 100 kilonewton or 100 ton, for example. And from the 30%, this is the column here, and 30 ton comes here. So the effect is going to be, the design force for this column is going to be 100 plus 30, which is 1.30. But the analysis can be done independently. That's the meaning here. The other way, the other option for this seismic design C, simultaneous application of orthogonal ground motion. The structure shall be analyzed using the linear response history or nonlinear response. Take care here. Nonlinear is applicable here. It was not applicable here. Here only it is linear response history. Here it is nonlinear response history procedure, as permitted by section, with orthogonal pairs of ground motions, acceleration histories applied simultaneously. This means that no way. You have the building, you need to apply 100 earthquake, 100% of the loading from here, and this is we are talking about analyzed using linear response history or nonlinear response history, using linear response history procedure or nonlinear response history procedure. So this in linear or nonlinear time history response, we need to apply because we have two components, okay? We have always two components for the same earthquake. If you are going to obtain it from pier, for example, then 100 of the component in X and component in Y, if we're talking about fault normal and fault parallel. So this is going to be applied on the structure simultaneously. So it is only for linear and nonlinear time history response analysis, which is not commonly used by the people actually. But for analysis and research that we are using it, so it is very important to consider that. For nonlinear time history analysis, which is commonly used for research, and linear response history analysis, so the orthogonal pairs of ground motion acceleration histories applied simultaneously in the same time. However, in equivalent lateral force resisting system, if it's applied with seismic design category C and type 5 irregularity, in this case we are going to apply 130% independently, but the force is going to be added together. The force is going to be added together. Okay, and the last thing is the seismic design category D through F, D and E and F. Structures assigned to seismic design these seismic design category shall as minimum conform to the requirements of the previous one, which is 12.5.3, the previous one, which is this one, this criteria. In addition, any column or wall that forms part of two or more intersecting seismic force resisting system and is subjected to axial load due to seismic forces acting along either principal plane axis equaling or exceeding 20% of the axial design strength of the column or wall shall be designed for the most critical load effect due to the application of seismic force in any direction. This means that if we have a plan and we have a column here, so if you are applying the load here or here, you're going to find that there are like if it's part of the lateral resisting system here and part of the lateral resisting system here, then you need to consider this and consider this section, okay, which is, as they said here, it is intersecting. If we have wall or column forms part of two or more intersecting seismic force resisting system and is subjected to axial load due to seismic force acting along either principal plane axis equaling or exceeding 20% of the axial design strength of the column or wall shall be designed for the most critical load effect due to application of the seismic force in any direction. Either of the procedure, section 5.3 and 5.3 A and B, the previous one, are permitted to be used to satisfy this requirement. This means that it is allowed for you to use the previous slide sections, okay, which is perpendicular, together, simultaneously or independently, and adding them up, except as required by section 7.3, 12.7. 2D analyses are permitted for structures with flexible diaphragms. 2D analyses are permitted for structures with flexible diaphragms, and this is understandable because flexible diaphragm, they are not going to be rigid and they're not going to connect together. Okay, I think that this is the last thing. Already this is a kind of repetition for what I have explained in the code, which is 100% and 30% for SDC. Okay, so already we have read this and we mentioned about it. This is the end of this video. Thank you very much and see you in the next video.